Dear students, in this topic, I would like to share principle of adiabatic demagnetization and Joule-Thomson cooling by using Maxwell's relations. Dear students, in the previous session, we learned about the temperature of inversion. Let us see what do you mean by adiabatic demagnetization. Let us see the principle of this. When a paramagnetic substance is magnetized, then external work is done on it. Then its temperature rises. When the substance is demagnetized, work is done by the substance. Hence, if the substance is demagnetized adiabatically, its temperature falls. When the substance is demagnetized adiabatically, its temperature falls. This is called adiabatic demagnetization. Maximum cooling can be produced by applying strong magnetic field and low initial temperatures. This is about adiabatic demagnetization. This is the totally principle of adiabatic demagnetization. Let us see the explanation regarding adiabatic demagnetization in brief. Generally, the method used to reach the very low temperature of about 10 to the power of -4 Kelvin is adiabatic demagnetization. In this method, the paramagnetic samples such as gadolinium sulfate is placed surrounding the gas sample and cooled to about 1 Kelvin along with the gas in any one of the cooling methods. The paramagnetic sample is used in this method is suddenly magnetized by the application of strong magnetic field. This magnetization, that means ordering of molecular magnets, is known as magnetization. This magnetization occurs while the sample surrounds the cooled gas and has thermal contact with the walls of the container. When the magnetic field is suddenly removed, then demagnetization occurs, which brings in a disordered state of the molecular magnets. To reach this state, thermal energy is taken away from the cooled air such that its temperature gets further lowered. By this technique, temperature as low as 0 Kelvin can be reached. Then it is said to be adiabatic demagnetization. Let us see the Joule-Thomson cooling by using Maxwell's relation. Dear students, it is seen from Joule-Thomson expansion that although there is a pressure difference on the two sides of the porous plug, the enthalpy of the gas remains constant. That is, enthalpy, which is indicated as H, which is equal to sum of internal energy and the product of pressure and volume. That is, H equals U plus PV, which is equal to a constant. On differentiating the above equation, we get dH equals du plus P dV plus V dP, which is equal to 0. That will be equation 1. But du plus P dV equals dq, which is also equal to T into ds. Here du plus P dV equals du is which is from the first law of thermodynamics, and dq equals Tds from the second law of thermodynamics. From both the laws we get this equation. Therefore, in the above equation 1, dH equals du plus P dV means dq here. Du plus P dV is written as dq plus V dP as it is, which is equal to 0. Or TdS plus VdP, because dq from second law of thermodynamics, dq equals TdS, the entropy concept. Here dq is replaced with TdS plus VdP, which is equal to 0. Let it be equation 2. If we take entropy, which is indicated by S, this entropy as a function of two independent variables like pressure and temperature, P and T. That is, S equals F of Pt, function of pressure and temperature. The entropy is a function of pressure and temperature. The change in entropy ds can be expressed as, that is, derivative of this one is ds equals dou S by dou P as a function of temperature into dP plus dou S by dou T as a function of pressure into dt. Therefore, we just substitute this in equation 2. We get the equation 2 ds is like this, T into dou S by dou P into dP plus dou S by dou T into dt plus V dP. This is T into ds. ds is from this equation substituted here in equation 2, which is equal to 0. Or just multiply T, open this flower bracket, T into dou S by dou P into dP plus T into dou S by dou T into dt plus V into dP as it is, which is equal to 0. Let it be equation 3. Now T into dou S by dou T, which is equal to dou Q by dou T, that is equal to Cp. That is specific heat of gas at constant pressure. And by Maxwell's fourth relation, thermodynamic relation, that is dou S by dou P as a function of temperature, which is equal to minus of dou V by dou T as a function of pressure. This is Maxwell's fourth relation. Let it be equation 4. Using equation 4 and 3, using equation 4, the equation 3 becomes, you just substitute dou S by dou P value like minus dou V by dou T in equation 3, we get minus T of dou V by dou T into dP plus Cp into dt plus V into dP is equal to 0. Therefore, Cp dt is equal to the remaining terms, these two terms comes towards RHS side. This negative sign becomes positive, that is T into dou V by dou T into dP. V plus VdP becomes minus VdP. This is the value of Cp dt. Again, the Cp dt equals T into dou V by dou T minus V into dP. Here dP is taken outside, then it becomes like this. Let it be equation 4. The Joule-Thomson cooling, that is delta T equals 1 by Cp. Here delta T is said to be, that is cooling temperature, that is known as Joule-Thomson cooling. Just to cross multiply Cp, then it becomes 1 by Cp into the remaining equation remains the same. The RHS of the equation 4 remains the same, that is T into dou V by dou T minus V into delta P. Let it be equation 5. Hence, this is Joule-Thomson cooling, that is equation 5. Therefore, the Joule-Thomson coefficient, that is coefficient is indicated by the symbol mu, that is mu equals dou T by dou P. This is Joule-Thomson coefficient, the ratio of dou T by dou P, which is equal to the RHS of equation 5 remains same, that is 1 by Cp into T of dou V by dou T minus V. This is equation 6. This is Joule-Thomson coefficient here. Here just delta P here in the equation 5, just cross multiply, that is taken towards LHS, that is delta dou T by dou P. This ratio is said to be Joule-Thomson coefficient. This expression gives the change in temperature delta T, change in temperature delta T of a gas due to Joule-Thomson effect. The enthalpy H remains constant here. In the process, the enthalpy remains constant in this process, and delta P is the pressure difference on the two sides of porous plug, which is necessarily negative as pressure on the emergent side of the porous plug is lower. Next, let us see what is the difference between the Joule-Kelvin and adiabatic expansion of a gas. In Joule-Kelvin expansion, the cooling is produced mainly due to the internal work done by the gas against the molecular attractions. The contribution of the next external work may be a cooling or heating effect depending upon the initial temperature of the gas. This is about Joule-Kelvin. Next, what about adiabatic expansion? In adiabatic expansion, the compressed gas is suddenly released to its atmosphere when it performs external work against the pressure of the atmosphere. Since the expansion is sudden, no appreciable heat flows into it from the surroundings. Hence, the external work is drawn from the internal energy of the gas itself, which therefore cools the gas. Thus, in adiabatic expansion, the cooling is mainly due to internal work. These are all the difference between Joule-Kelvin and adiabatic expansion of gas. Thank you.